Hello, class. Welcome back. This is lecture 7. Today we are talking about geometric series. We might do more, depends how long it takes. But first, we're actually going to talk about some rules that work for series in general. So these come in handy. And then after that, we'll talk about the title, which is the geometric series. Okay, so here are some rules. All these rules come from the fact that we're really using limits. So this first one is, if you have a series and you have two things added together in the series, then you can split it up and do each one independently. Or you can go vice versa. If you have two that are separated, you can put them together. And so you need them both to converge for this to work. But so for example, one way we could use this is for something like this. So we already did these two in a previous video. We've done these two independently. So this one is a little bit different than the one we did, but it's actually the same. The point is, though, that you can split it up because we know how that each one independently converges. So this converges, this converges. The second one, I believe we did in the last video, and it was convergent to 1. So that's just 1. And the other one, maybe we did in the last video, or maybe one before that, but it ends up being 2. And it's because it's the same as this. If I start counting from 0 instead, then I have to adjust the index, which I'll talk more about in a second as well. But if I want to start at the same place, then now this needs to be an n. And that's what we saw was 2 before. And it's the same as that. But the point of this is that you can break it up into 2 pieces because they both converge individually. So that's a general rule you can use. And it really just comes from limits. Another rule is that you can pull out constants. Also comes from limits. So we're not really going to prove these rules. But we're going to sort of take them for granted. So for example, if I had this, then because the 3 is not changing with respect to the index, there's no n on the 3, I can really just take it out and I can just deal with the series now that I know how to do, which again, that's just 2. So then I get 6. The other way to think about it is like, this really means like 3 times 1 over 2 to the 0 plus 1 over 2 to the 1 plus 1 over 2 to the 2 and so on. And of course, that's the same as if I have it on the inside. Then I'm just multiplying 3 to each thing individually. So it's really like I'm just factoring out the 3. That's why you can take a constant out like this. Okay, so we're going to use that a lot. That's probably the most useful one. And the last one is adjusting the index, which I already sort of did. So maybe I should have done this one first. But we've actually used it before in the lecture problems. And it goes something like this. If you want, you can rewrite your sequence starting at a different number. Really, you can pick any number you want. So like you could pick 10 here, but you have to do the opposite adjustment to the actual variable in the series. So basically because I added 9, if I still want to start at the same place, I need to subtract 9, right? So now these still start at the same place because here, when I plug in 1, I get 1 over 2 to the 1 is 1 over 2. So that's the first thing in the sum. So if these are to be the same, this better be the same starting thing. And it is, because if I plug in 10 here, I get 1 over 2 to the 1 still. So yeah, they start at the same place. So that's the adjustment. So whatever you add, you have to subtract, and vice versa. So if I subtract, I could do that too. If I have like something like this, if I want to subtract 5 from the index, then I have to add 5 to the n to make up for it. So that rule is also very useful. So keep those in mind. Okay, so now we are ready to move on to type of series. So far we've just thrown out a couple series and did some examples, but what we really do in this class is we sort of categorize various types of series and try to understand them all at once. So let's think about one of these types, which is called the geometric series. So it's not going to be something very particular. It's going to be any series of a certain form, the form being something like this. So it's got to have a number to the nth power, and you can multiply by a constant if you want. So it'll look like this, like c times r to the 0 plus c times r to the 1 plus c times r to the 2, and so on. But because of that rule we just said, you could also just take the c out and write it like this, and that's fine too. Okay, so a geometric series is one that looks like this. So r and c are just numbers. They are particular numbers. So for example, we've actually done one like this. So this doesn't look exactly the same until you rewrite it a little bit. Yeah, the way to realize that it's the same is to know that a 1 is the same as a 1 to the nth power, right? Those are the same because 1 times itself a bunch of times is still going to be 1. So then what you can do is take out the nth power and write it like that. And so now it's a geometric series where r, so it's a geometric series where r is 1/2 and c is just 1. There's an invisible 1 there that you never write when you're multiplying by 1, but it's there. So yeah, this is an example of a geometric series. We've already worked with one of them. This is another. Maybe this time I'll just put it already in the nice form. So this is another geometric series with r being 1/3 and c being 5. Okay. So these series are especially nice. We can figure out exactly when they converge and when they diverge. So you can't just do that for any series you think of. So the point of classifying them is, well, maybe if I just limit my scope to just a couple series, maybe I can figure out those ones. And that's exactly what we can do here. So we can actually determine when a geometric series converges or not. It turns out to be pretty simple. We already know 1. When r was 1/2, we ended up with converging to 2. That's we did that the other day. So that's this one. So we said that this turned out to just equal 2. So for r being 1/2 and c being 1, we know that it converges to 2. Okay. So maybe that'll hint at what to do. Let's see if we could figure out some other ones. What about if r is 1? Well, then we get something like this, c times 1 to the n. What would that be? That would just be c times 1 plus c times 1 plus c times 1 plus and so on forever. Does this converge? No. Why not? Well, we're just adding up a number a bunch of times, but you can also think about it as like, if I just add the number 1 a bunch of times, that's already too big to converge. That's already going to add up to infinity. So no, this diverges. And if you want to use the partial sums to be very precise about it, what would S1 be? S1 would be, so I guess it would be like c times 1 plus c times 1, because we're starting counting at 0. S2 would just be c times 1 plus c times 1 plus c times 1. And what would Sk be in general? Well, it would just be c times, so how many 1s are there? There's always one more, k plus 1. But then if I took this limit as k goes to infinity, well, there's nothing on the denominator to make this shrink to a number. So it's just going to grow and grow because k gets very big. It's going to go to infinity. So yeah, this will diverge when r is 1. And it really doesn't matter what c is. I guess if c was 0 is the only way it would be 0. But other than that, it doesn't matter. So the same would happen if you made r be any bigger. So if r was any bigger, all that would happen would be that this would be even bigger. Well, it's already going to infinity, can't get much bigger than that, so it's still going to diverge. So and you could just say if r is greater than or equal to 1, it will definitely diverge. So we figured out some answers. What about if r is less than 1? Let's think about that next, because 1/2, that was great. That one made it converge. So maybe other things less than 1 would also be good. So let's think about being between 0 and 1. Well, then this all looks the same. So S1 would be c times r to the 0 plus c times r to the 1. S2 would be c times r to the 0 plus c times r to the 1 plus c times r squared, and so on like that. Sk would be, well, let's factor out that c. And then I have 1 plus r, because r to the 0 is 1, plus r squared plus ... plus, and I guess we always go out to the same power, so it'll be r to the k. So Sk looks something like that. And I want to be able to take this limit, but I don't have a nice formula for Sk yet, but we're going to use some algebra tricks to figure out a nice formula. So the idea was before that when r was bigger than 1, this just gets really big, it goes to infinity. But now when you're between 0 and 1, when you're like a tiny little fraction, it might not do that. And let's see why not. So here's the trick to this problem. It's purely a magic trick. We're going to multiply both sides by 1 minus r. So we get 1 minus r sk equals 1 minus r c, 1 plus r squared dot plus r to the k. So it looks like we just made it more complicated instead of making it easier. And then on the right side, let's distribute this through. So how's that going to look? Well, you can think about it as this whole big thing times 1, which just is another copy of itself. So the c we're leaving on the outside. So 1 times this whole big thing doesn't really do anything to it. And then distribute the minus r through. So minus r times 1 is r. So it's just going to add an extra power of r to each thing that's already there. So r plus r squared plus r cubed. And then the last one will now be r to the k plus 1. That one gets 1 extra power of r. So then we're here. And what's going to happen when I minus each of these? Well, a bunch of them will cancel. So r minus r is 0. The next one, r squared, which is in these ellipses, will cancel with r squared. The r cubed will cancel with r cubed. They're all going to cancel except this one didn't have any pal to cancel with. And this extra r to the k plus 1 doesn't have anyone to cancel with, but it still has this minus. So it's minus r to the k plus 1. So that's what the right side turns into. On the left side, we still have this, didn't do anything. And then we're just going to divide by 1 minus r on both sides to simplify and solve for sk. So now we have a nice little formula for sk. And once you have your formula for sk, you can, that's how you find the sum of the series, is by taking the limit of this thing. So let's do that. So then let's take the limit. As k goes to infinity. Well, it looks tricky, I guess, but you have to remember what kind of number r is. So it's because r is a fraction between 0 and 1 that when you raise it to k and make k go to infinity, that's going to go to 0. So for example, 1/2 to the k plus 1, that goes to 0 as k goes to infinity, because the 1 is really not changing, and the bottom is growing faster. And this will happen for any fraction between 0 and 1. The bottom will go faster, and this will go to 0. So what happens is this thing just goes to 0. So you just get c times 1 minus 0 over 1 minus r. Oh wait, sorry, I already took the limit, so that's gone. There's no k's anywhere else to take the limit, so you really just get this. So this is, remember, that's the definition of the series, of what the series adds up to. So this is, in fact, what our series adds up to that we started with. Okay, so this also works for negative values. You can do the same type of thing. So if you have negative fractions, it works too. So in general, we could just say that if your R is between 1 and -1, then your geometric series will definitely converge, and specifically it'll converge to this thing. This is what it actually equals. So it converges to that. Otherwise, if R is outside of 1 and -1, then it'll diverge. Okay, so that's the solution for all geometric series. So it's pretty nice. So we can solve a whole bunch of series problems all at once now. So for example, something like this. Why don't we just test out our little formulas for something that we already know? This is supposed to be 2. But now let's use the formula. So C is 1, 1 minus R is 1/2. So you get 1/2, which is in fact 2, which is what we got the long way. But this is much faster. But again, you have to use the right tools for the right situations. So this only works for geometric series. For some other weird series, you wouldn't be able to use this formula. So just keep that in mind. Yes, it's quick, but it only works for specific things. So this would be something like this, would be 4/1 minus 1/7. I don't want to simplify, so I'll just leave it like that. Okay. And then the only thing we have to do is worry about using the adjustment of indices if the index starts at a different place. So for example, if I do something like this, where I start at 5, I can still use the same formula if I first adjust the indexed. So I need to adjust the index for it to work. So it has to start at 0 for me to use this formula. So I change it to 0, but then what does that do? Well, that subtracts, or sorry, I subtracted 5 from the index, so I have to add 5 for it to still be the same series. And then it's still not exactly in the right form because we have this extra +5 here. We don't want that. So then what we have to do is remember how powers work and realize that that is just the same as 3/8 to the 5th times 3/8 to the n, because if you have the same base, you add the powers. And then I can use my other rule that says, well, these are constants. They don't have any variable in them. There's no n in this piece of this that's being multiplied. So because it's being multiplied, I can just factor it out. And then I'm now left with something that I can use my formula on to finish the problem. So this guy is a geometric series now, with R being 3/8. So I can use the formula. C is just 1 because I took all of the constants out. I could have just left them in there and called them C, and that would also work. But I chose to do it this way, and that's okay. All right, so this is just going to be 1/1 minus 3/8. And then there's no need to simplify. We can just leave it like that. Okay. So yeah, you could do lots of variations on this type of thing. So maybe I'll do a couple more. So you could do something like start at a negative index, and maybe we could stick a negative in here. That doesn't really matter. And you could even start at a different index there. You still have to identify that this looks like a geometric series, and maybe I'll add another piece. So this is still a geometric series problem. And the basic way to identify it is because you still have a number to the nth power, but it's just got some extra gizmos on it. And as soon as you see that, you should be able to recognize, hey, this is going to be a geometric series, but I need to adjust. So what can we do? Well, we can use that first, I think it was the first rule I said, which is you can split this up into two problems because they're both geometric series. And the fractions are less than 1, so they're both going to converge. So we can just do them independently. Now we need to adjust the index on both of them. So they're both wrong at the same place, but it could be a different problem where you have two different indices that you have to adjust differently. But in this case, I need to add 2 to both of them, which means I'll need to subtract 2. Oops, that was a 5 there. Which means I'll need to subtract 2 to the variable that's changing. So this will become n minus 4. And then this one, same thing. I need to subtract 2. So this will become n minus 2 plus 1 is minus 1. And then I have to take out the extra constants. So this minus 4 just means I have a minus 4 power being multiplied to the nth power of the same base. And over here, I just have a 1/4 to the negative 1 power being multiplied. And now I can just take out all the constants that I don't want. I don't have to simplify this. You can simplify it if you are feeling cool, I guess you could do it, but it's okay. The more you simplify, the more opportunity there is to make a mistake. So I prefer only to simplify if I need to use it for something else later. But if this is the end of the problem, then why bother? Okay, and it is just about to be the end. So now, because I have my geometric series in the right form, I can use my 1/1 minus r formula to finish the problem and say that it converges to this. Okay. I don't need that many parentheses, but whatever. Looks nicer, I guess. Okay, so that's what the original thing converges to that we started with way up here. This converges, and it specifically converges to this big old number here, whatever the heck that is. Okay, so once again, this formula, just last thing, it only works for geometric series. So for example, this is not geometric. It might trick some of you because you might see an n and a power, but that's not the same as something like this. This is geometric, where r is 4, and because it's bigger than 1, it diverges. So we won't have to do anything else. We can just say it diverges because it's bigger than or equal to 1. Okay, so that's going to be it for geometric series, and I'll see you next time.